Alright, hello, sorry I couldn't be here today. This is the lesson for Introduction to Vectors. One thing, sorry I'm super early in the morning, so if my voice is a little cracky, sorry about that. And two, I don't have a stylus, so I'm going to be writing with my finger. I think I should be able to do well anyways. Okay, so let's quickly talk about what vectors are and then move forward with the lesson. A good amount of you have seen vectors within physics. Vectors are a line segment that has a beginning point and an ending point. Obviously it's a segment, but it indicates direction and how far something is moving. So imagine you have like water flowing in a river, and if I drop a piece of sand, you think of an object that's only affected by the flow of the water at any point in the river. It's going to travel in a direction with the water, and it's going to travel a certain distance. And so the vector represents the beginning point is like where you drop the sand, and the direction of the arrow says which direction that sand would go, and the length of the vector represents how far it would go per unit of time. So just imagine, like, let's say if I drop the sand there and it would go in that direction, and in 1 second it would go that distance. Now you can imagine if we dropped a grain of sand there, and that was the vector representing that spot, then that piece of sand would be going essentially in the same direction as that other one, but it wouldn't be going as fast. If we look at, for instance, over here, we could have a vector going in this direction, then that piece of sand would go in that direction, and that far from the beginning point to the end point in that amount of time. So that's the basics of what a vector is. And now we'll get into kind of the more the details of how we're going to be working with a vector. So imagine we have the point 2, 3 and the point 5, 6. And let's say my vector starts here at the point 2, 3 and goes to 5, 6. Actually, that should be 3, 2. My apologies. So, how far did it move in the x and how far did it move in the y? So, first off, there's different ways we can label this. We could call the whole vector u. This is point P, this is point Q. We could also call it PQ. So, the vector is called PQ, or it is just called u. Another way we could do it was with a bold u, okay, which is kind of hard to write, but you see that a lot in the book. Okay, so the next part is talking about if we're adding two vectors, and this goes to the idea of when we have two objects with some sort of movement, we want to figure out if an object was within that system, how it would move. So a good example of this is the conveyor belt at the airport. Like if we're walking down the terminal and we have the conveyor belt on the ground that helps us walk faster. So imagine we're walking in that direction. That's a vector that we're walking. So for instance, we're saying we're walking 2 in the x direction. Okay, I'll write it out. Let's say we're walking 2 in the x direction, 2 feet per second. We're walking on the vector 2, 0. And then the conveyor belt's moving 3 feet per second in the x direction. That would mean when we walk on top of it relative to the ground, we'd be adding them together and we'd be walking 5, 0. And that's why it's kind of fun, because we feel like we're walking 2 feet per second, but relative to the ground, we're really walking 5 feet per second. Now the other opposite example would be a treadmill. Let's say I'm running 5 feet per second in the x, just the x direction, just keep things simple. Well, the treadmill is not going with me, it's going against me. And if we're running in place, it's because the treadmill is going the exact same speed in the other direction. So that would be negative 5, 0. And if we add that together relative to the ground, we're going 0, 0. So that's the basics of vector addition, but that's when the vectors are going the same direction or opposite. What happens when they are going in some like oblique angles? So that's what we have with U. So imagine U is me walking, and V, imagine, is a vector representing like the whole floor. The whole floor everywhere is going in that direction. It's like a moving slated floor, I guess, or like in all directions. But we do have that vector right there and this right here. And just like if I have the conveyor belt or the treadmill, that vector would be going in this direction as well, or going in that direction. We would want to bring these together, because just like if I'm walking on this and this is a conveyor belt going that direction, it doesn't matter if that conveyor belt is going everywhere in that same direction. I can take these two vectors together. So that's the first thing we do. We take the u vector and we put it with the v vector. And then what we do is, we know that this is how we're moving, but we also have the v moving us along as well. So you can imagine, relative to the stationary floor, it would, the addition of the two of them would be the path that we are taking. And so what essentially you're doing is creating a parallelogram. Here is our u, here is our initial v. We can do what's called parallel transport and take this vector, move it up here, take this vector, parallel transport it here, and then the diagonal of that parallelogram is the new vector, in which if I'm walking on this conveyor, you're walking on this conveyor belt floor, and you're walking along this path, it's moving along this path. This would be the path that you take relative to the stationary ground. A couple of things extra. We can talk about scaling a vector. So imagine we're going in the same, or we're going in the opposite direction. So if I have a vector v, let's say I'm walking in this direction at that magnitude. Let's say still I just slow down my speed by half, then my vector would look like this. And note the beginning point's here versus right here. That's not the important point. The important thing about vectors in terms of where they start is more important about the direction, the magnitude of it. So this is representing a vector going the same direction, but just going to half speed. This would be double the initial. This would be going the same velocity, or the same speed, same magnitude, but going in the opposite direction. So it's just basically like I turn around and go the exact same speed. And this would be turning around and going 1.5 times faster. So a couple of things. First off, definition of vectors. If you can imagine, if we are adding these two vectors, we're simply adding the components. You can see if we, the x value of u, right, right here is like negative 1-ish, right? And then for this vector v, if you look, that's like maybe 4. Oh, I'm sorry, not where this initial point is, my bad. Looking at this vector, how far that moves in the x direction. It's like maybe 2, and then v moving in the x direction is maybe 4. This would be the addition of them, which would be 6, and then the same thing for the y's. So vector addition is quite simple. All you're doing is adding the x components and adding the y components, and then if we're scaling it like this, all you're doing is you're taking that scalar k and multiplying it by the component vector, right? The brackets there, and there's our x value and the y value, and you're just taking that scalar and multiplying it by both of them. That's it. Okay, so you're gonna just maybe do a couple of these geometric diagrams with vector addition. So we have 2, 3. I'm going to graph the vector 2, 3. It really doesn't matter where I graph it. Over 2 and up 3 would put it right there. So there's my v vector, and I'm not even going to write v. I am going to write u now. That's my u, sorry. And now I'm going to graph v, which is 3, 1. So now with that same initial point, I have that. Now I'm going to create, and again, it doesn't matter where on my coordinate system I put it. Okay, now what we're going to do is parallel transport. Let me clean this up a little bit. Okay, so we are going to parallel transport. So my u vector, which was 2, 3, I'm going to start that right here now and go over 2 and then up 3. And then my v vector, which was 3, 1, I'm going to start here and go over 3 and up 1. And you see we now have our parallelogram, and our new vector, which we call u plus v, would be right there. That's geometrically how we would do it. As far as doing it algebraically, we would simply add the two together. So we'd have this new vector u plus v, and we could call it w, you could call it z, or you just call it u plus v. It would be 5, 4. And we could look over here that this new vector, if we looked at the components of it, 5 in the x direction and 4 in the y direction. What would u minus v look like? This one's a little more difficult, but u minus v, u is still 2, 3. So let's just go and graph u anywhere. Start here and then go up to 1, 2, 1, 2, 3. There's u. And now we're going to graph v first, which is 3, 1. I'm going to do that in red. 2, 3, 1. Now that's v, but that's not what we want to find. We want to find u minus v. We're going to treat u minus v as an addition of u plus the opposite of v. And then we're still doing vector addition. We just got to figure out what opposite of v looks like. Let's come over here. So again, the black is u, and then the red is v. We don't want to graph v, we want to graph the opposite of v, which would be going the same distance but in the exact opposite direction. So instead of 3, 1, we have negative 3, 1, which would put us there. That would be negative 3, negative 1. Just go to that point right there. And now you can disregard looking at this, and we are going to create our parallelogram from these two right here. So this vector right here, which is 2, 3, we're going to start here, just like we did on the other diagram. We go to this endpoint and parallel transport this vector over here by starting at this point. So now again we have 2, 3, so we start here and graph 2, 3, 2, 1, 2, 3, and do the same where we start at that endpoint right here and graph the parallel, or I'm sorry, start at this endpoint and graph the parallel transport of this vector down here, which is negative 3, negative 1. Go negative 3, negative 1 puts us there. Our initial point where we started is going to be our starting point for the resultant, or the addition vector, to the point where those two parallel transported vectors combine together. And now we look at the components of this. This is displacing the x by 1 and displacing the y at 2, and therefore that new vector would be negative 1, 2. Okay, that's all for this. Do the best you can, and I'll see you all on Wednesday. Have a good day.